This is Chemistry CP on Friday, November 20th, 2020. I'm presenting Electron configuration PowerPoint with some exciting narration to kind of explain the slides as you see them. This is a photograph of a student's sheet of paper generated at an activity that you would normally have done in class during a regular school year. The center of the graph paper represents the nucleus of an atom. The way this activity is done is pairs of students are giving dice, that which you use when you go gambling and it's got 6 sides on it and you roll the numbers and hope you get lucky. The dice has been modified. Instead of having 1, 2, 3, 4, 5, 6, it only has 1, 2, and 3, with a certain number of sides allocated to each of those 3 possibilities, 2 being the most frequent occurrence. If you roll a 1, then you mark off on the graph paper a certain short distance from the nucleus of the atom. If you roll a 2, you mark off in a larger range of distances from the center of the atom 1 square and fill it in. If you roll a 3, you mark off the greater distance from the center of the atom and fill in 1 square that way. You roll the dice 50 times. After doing it 50 times, you tend to create a pattern that looks somewhat like this. This represents 1 atom, and each colored square
We can't see what you're presenting.
Oh! I'm going to pause in this presentation. Oh man, I can't even pause. I'm going to exit this presentation. Oh, that's great. Drats. All right, as I was starting to explain, when you look at this photograph of a student's graph paper, the center square represents the nucleus of 1 atom. Each colored in square represents the possible location of 1 electron at a given instant in time. The pattern that's starting to emerge from this suggests that most of the time, the electron is some distance away from the atom, sort of like the dark purplish colored squares. Occasionally, it's a little bit farther out, represented by the green colored squares. And sometimes it's closer to the nucleus, represented by the filled in squares closest to the center. The point of this exercise is to get you students to recognize that an atom is not a definite hard spherical shell. It is a fuzzy, diffuse cloud of probability of, 90% of the time, you're probably going to find the electron within this particular radius. But even that isn't set in stone, so to speak. The electrons are whizzing around, and at any instant, they could be at one of these particular dots. Where is the highest probability of finding this electron? Where the dots are the most filled in. Now, keep in mind, you're looking at a 2-dimensional sheet of paper that's really trying to get you to visualize a 3-dimensional sphere. All right. Last period, I asked students to unmute and tell me what did they infer about this design. Today, this period, I'll spare you the interrogation and tell you these dots represent a little bit higher quality modeling by a professional chemist of the probability distribution function for a single electron orbiting a single atom nucleus. Whew! What does that mean? It's the same thing as the previous slide, but done on a computer. It's a two-dimensional map of a three-dimensional sphere. The closer the dots are to each other, the greater the probability that that is where you would locate the electron. Where the dots are spread farther apart, it's less likely, but not impossible, that that would be where you find the electron. This model suggests that it's most likely to find the electron close to the nucleus of this atom. But again, it's a 90% probability. In terms of physics, the electron speeds up as it moves closer to the nucleus, slows down as it moves away from it, at least in classical physics. And therefore, it's less likely that you find it closer to the nucleus, even though it's more likely to be closer to the nucleus. Or something like that. Too bad I can't delete that line, huh? This is the same concept, only now, instead of dots that you can see still, the dots are smaller in size and more dots. So it's become just a cloud, a gradation. Where the cloud is darkest is closest to the nucleus, and that is where the probability is highest of finding this electron. We're always looking for this electron. Now, here is a rhetorical question. How are the electrons placed into atoms? Meaning, where are they located as you place them, as you arrange them around a given atom? The answer is complicated. And I'm going to spend all period trying to have your understanding evolve on how to carry out a complicated procedure of arranging electrons around atoms. First, every atom contains energy levels. We call that the principal quantum number or principal energy number. It begins with n equals 1, and this corresponds to the top of your sheet of paper when you look at the periodic table. The elements hydrogen and helium are in the n equals 1 energy level. Below that is energy level 2, lithium, beryllium, all the way to neon. N equals 1 with hydrogen and helium is the lowest energy level, closest to the nucleus of the atom. As you go higher energy levels, you are also moving physically farther away from the nucleus. The radii of the probability distribution function of where you're likely to find the electrons increases in value as the principal energy level increases in value. Whoa, the higher the energy, the farther away from the nucleus you're going to find the electrons. But wait, there's more. In addition to each principal energy level, there are subshells. I'm going to try to slow down my talking a little bit because I do see there are some students who are taking notes. I have just posted this PowerPoint as a PDF on our Google Classroom. However, if truth be told, you do learn material better if you write down notes as we go along. So I'll try to accommodate the students I see who are taking notes. And this does become quite a bit more complicated. So the first order of business is the energy level. Every period on the periodic table, that means every row, corresponds to an energy level. There are 4 different subshells. To explain how they got their letters, so we use a letter for each one of the 4. Imagine looking at a rainbow. You see the colors of the rainbow. We have students memorize it as Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. Now, what if you could zoom in on just one color? Take orange. You zoom in on it, you look at it, spread that orange out a lot, and zoom in and look at each little tiny variation in the shade of orange, from red to yellow, all the different shades of orange. Now zoom in even more. An instrument that spreads apart the colors of the rainbow is called a spectroscope. And the people who study the light that they see in the spectroscope, why, that's called the study of spectroscopy. And they are spectroscopists who are studying spectroscopy using spectroscopes. Wow, say that 5 times fast. When they look at the light, at the colors being given off by glowing elements, they noticed 4 different types of features. The first one is that some of the colors, and by the way, in a spectroscope, these things appear as lines of light, little vertical lines of light as you look into the instrument. So some of the lines of light looked very sharp compared to the others. And that's where they got their name as being called the S subshell. So S stands for sharp. The spectroscopists were studying light. The chemists were studying atoms. Between the 2 groups, they figured out how the light decodes the structure of atoms. So it was really necessary to do spectroscopy to figure out atomic structure. So one set of lines always looked very sharp. Another set of lines looked like they had a very repeatable, predictable, mathematical pattern to them. Sort of like 1 over n. 1 over 1, 1 over 2, 1 over 3, 1 over 4. That's a pattern when you graph it. Well, these lines had that kind of recognizable pattern to them, so they called them the principal lines, not the pattern lines, the principal lines. Meaning, oh man, these look like they're the main ones that help explain the whole idea of what's going on. Those are the P subshells. The third set of lines looked blurry. And of course, we don't call them the blurry lines. That doesn't sound very scientific. So we call them the diffuse lines, D is for diffuse. They would look blurry, is what you would say. Not sharp at all, and not in the pattern of the principal lines. They would just say, oh, here's a shade of orange that's glowing that is kind of blurry. Here's another shade of orange. Maybe this one's purple even. Okay, it's not just one color. Spectroscopy is spreading out the entire rainbow so that you can look at very specific colors in detail. Okay, we actually do it to a scale and say, oh, here's the wavelength of this light. Here's the wavelength of that light. Different wavelengths correspond to different colors. And we can break it up into millions of wavelengths. The last set of lines that they see in spectroscopy, are called the fine lines. And by fine, we mean faint, hard to even notice. They're so skinny when you look at it in the spectroscope. So F for fine. And that's it. Just these four groups. The sharp lines, the principal lines, the diffuse lines, and the fine lines. Those visual descriptors have become shortened over the years to represent the different electron subshells when we describe where to find electrons inside an atom. The S subshell, P subshell, D subshell, and F subshell. But wait, there's more. Each one of those subshells contains orbitals. And the reason it says is/r is because the first subshell, the S subshell, only has one orbital. All the rest have more than one. The reason these four are not listed in alphabetical order is because they are listed in the order of increasing number of orbitals. The S subshell has one orbital. P has three. D has five. F has seven. Okay, so it's odd numbers, 1, 3, 5, 7, in that order, S, P, D, F. But wait, there's more. These orbitals are where we find the electrons. Every orbital can hold a maximum of 2 electrons. I admire seeing students who look so diligent taking notes. Gives me a good feeling. Now, let's complicate things. It says here rhetorically, how are the electrons placed in the atom? And it says the periodic table will show you where to locate each energy level and subshell on your worksheet. Color the sections to represent the different subshells. What worksheet, you ask? The one I never gave you, I say. Normally, and here it is, normally we pass this out to our students during class. And over the course of multiple days, we have the students fill in the periodic table with ever more layers of information. It's educational to have you do that. Of course, you can be like me and just print a periodic table in color off the internet, and it has all that information. We would normally have the students do this by hand and then use different colors and highlight things. I've tried to call your attention in the past to the shape of the periodic table. It is not a simple rectangle. It's this funny shape with the two rows sticking alone by themselves underneath the periodic table, the two single boxes on the top row. Why? Why does it look like this? Here's the answer. Each color corresponds to a different subshell. Starting on the left, the two left columns correspond to the S subshell. Now, hydrogen, the top left one, goes, I think they mentioned in a video or PowerPoint, they weren't really sure where to place it. That was a YouTube video. Here's where we place it on the periodic table as an alkali metal. Helium is placed way off separately on top of the noble gases on the right end of the periodic table. We put all the noble gases on the right side of the periodic table. And what they have in common is that their subshells are completely full. That means they have no interest in giving up electrons or receiving electrons or interacting with any of the other elements, or with each other for that matter. Helium has a completely filled subshell. That's why it's labeled and displayed along with the entire column of noble gases. Okay, so that's that first color. In fact, I think the next slide labels the letters. Ta-da! Here's what I was going to say over the next 3 minutes. The dark purple block on the right represents the P subshell. S for sharp, P for principal. The light kind of bluish color where the transition elements go is the D subshell. And dangling separately below the periodic table, those two rows are the F subshell, periods 6 and 7. This is why the periodic table has the shape that it does. Let's complicate things. It's not confusing enough that this explains the shape of the periodic table. We want you to be able to correctly list the order in which these shells become filled with electrons. There is a pattern to it. Here we go. The drawing at the bottom is a reminder that these atoms are fuzzy clouds of probability distribution, meaning as you get closer to the nucleus, it's more likely than not that the electron is within that radius, but it's not a definite edge to it. What you can see with your eye here might represent the 90% radius value. The first discriminator is the energy level N, and that corresponds to each period of the periodic table. Within a given energy level, there are 1 or 2 or 3 or 4 sublevels. Each sublevel contains orbitals. Each orbital can hold no more than 2 electrons. Think of a house. We finally get to go on a field trip. Yay! And unfortunately, we can't afford individual rooms for every student. Boo! In fact, you don't even get your own bed. You're in a shared room with a shared bed, much as I had to do on my 8th grade field trip when we went to Williamsburg, Virginia. The bottom floor of this house represents the lowest energy level. This entire house represents 1 atom. And on the bottom floor, there's only 1 bedroom. That would be the 1s subshell. The second floor, and some people go ground floor, first floor, some people go first floor, second floor, whatever, the second floor has 2 bedrooms. One of them is the 2s subshell, and the second one is the 2p subshell. The third floor has 3 subshells, and the fourth floor has 4 subshells. Our 3-minute timer just went off, so I invite you. All right, back from break. As we look at this analogy using a house to represent the different energy levels of an atom, each room has at least 1 bed, and each bed can hold at most 2 electrons. Oh man, as I click forward, you can see the numbers appearing on the bottom right. So the first layer is energy level 1. The second floor is energy level 2. Then comes energy level 3, followed by 4. You can guess what comes next. 5, energy level 5. But wait, there's more. The first floor has a single room, and that is the 1s subshell. That room has 1 bed. That bed can hold 2 electrons. The second energy level has 2 subshells, the 2s subshell and the 2p subshell. The 2s subshell has 1 bed that can hold 2 electrons. The 2p subshell has 3 beds. Each bed can always hold up to 2 electrons. Therefore, the 2p subshell can hold up to 6 electrons. The third floor, the third energy level, has 3 subshells. The 3s subshell can hold 2 electrons. The 3p subshell can hold 6 electrons. The 3d subshell has 5 beds. Each bed can hold up to 2 electrons. So the 3d subshell can hold a maximum of 10 electrons. On the fourth floor, we have all 4 types of subshells, S and P and D and F. The F subshell has 7 beds, and therefore it can hold 14 electrons in the 4F subshell. The pattern suggests that the fifth floor should have 5 subshells, but atoms built that way are unstable. They don't exist. So we're limited to the 4 types of subshells, and the fifth energy level has the same set of 4 as the fourth energy level. This is going to become even more complicated. I've already answered this question, so it's somewhat rhetorical. How many beds or orbitals are in each room, which is really a subshell? And therefore, hold up your fingers, please, Giselle. How many orbitals are in the S subshell? I agree. How many orbitals in the P subshell, Jessica? Uh, 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 uh. Yikes. Oops. Put your hand where I can see it. And there, that is correct. Look at that. 3 orbitals in the S subshell. How many orbitals in the D subshell, Emmanuel? You have to hold your hand up where I can see it since you're pointing the camera at the ceiling. I cannot see your hand. I cannot see your hand. Emmanuel, Lorenzo. A child below the monitor. Okay. Now show me your fingers. Ooh, not that one. Oh, let's just ignore you. Okay, children, the answer is this much. And with just one hand, how many orbitals in the F subshell, Amber? It's got to be a mirror image of that. Going the wrong way. 7. There you go, finally. Now, each bed, I remind you, really represents an orbital. So the 1s subshell has 1 orbital, P has 3, D has 5, and F has 7. There's more. So how many electrons can you put into the S subshell? The answer is it has 1 orbital. Each orbital can hold 2 electrons. So therefore, you do the math. The S subshell can hold 2 electrons. The P subshell can hold, yes, 6 electrons. The D, of course, 10 electrons. And F, 41. Okay, 14 electrons. Okay, go look. Note now the numbers on the left, 1 through 7. The top row is 1. That's the principal energy level. So there are 7 energy levels on the known elements in the universe. The S subshell represents the 2 left columns. The P subshell, the 6 right columns. And for reasons I explained earlier, helium is added on the far right because its subshell is full, just like all the noble gases directly below it. Here's where the D subshell is. Here's where the F subshell is. Now think, children, think, how many electrons fit into the S subshell? Amber, again, visually. How many electrons fit into the S subshell? You're counting wrong. How many columns? No. Look carefully, children. There are 2 columns on the periodic table associated with the S subshell. There are 6 columns associated with the P subshell. There are 10 columns associated with the diffuse subshell. And by now you should be able to guess, there are 14 columns representing the F subshell. That is why the periodic table has the funny shape that it has. Your task is to become masters at expressing the order in which the subshells are filled with electrons. Oh my goodness. Here's a blank periodic table. The general order is to fill the subshells from left to right in order of increasing energy level. So we start at the top. This is like the first floor of that house. We completely fill the 1s subshell. Then we go to the 2s subshell. Then to the 2p subshell. I remind you there is no 2d or 2f subshell. Then it's 3s, then 3p, which is interesting because there is a 3d subshell, but we don't fill that before filling the 3d subshell. I'm sorry, 3p. P is in principle. Interestingly enough, we do 4s. Then this one is not called the 4d subshell. It's treated as the 3d subshell. How's that for craziness? Then the 4p, as in principal subshell. Then 5s, 4d, 5p, 6, 1, 2, 3, 4, 5, 6, s, and so forth. Great. I'll give you a visual later of that pattern. For now, recognize that the left 2 columns are the S subshell. The 6 columns on the right are the P subshell. The transition elements are the D subshell, and the separate chunk listed underneath the rest is the F subshell. They show here the names of the elements that occupy those spaces. This next slide shows which energy subshell corresponds to it. And let me toggle back and forth. So hydrogen, for example, the top left corner, is the 1s subshell. We use a superscript to represent the number of electrons in that subshell. So that's why it's S raised to the first power. We would call that the S1. Helium, on the top right corner, is 1s2. The second energy level begins with the element lithium, and that has its outermost electron in the 2s1 subshell. Beryllium would be 2s2. Boron would be 2p1. And then you can see how it fills in 1, 2, 3, 4, 5, 6 as you go across till you get to neon at the end of the second row. The third row, there's the S's. Over on the right, there's the P's. On row 4, there's the 2 S's, then the 10 D's, then the 6 P's, and so forth. Now, I forget what happens when I press this button. I did that. Here we go. This is the way that we write the electron configuration. The big number in front represents the energy level. So it can be 1, 2, 3, 4, 5, 6, or 7. Then we write the letter, always lowercase, of the subshell. S for sharp, P for principal, D for diffuse, F for fine. And of course, in modern times, you students basically don't even learn that that's what the letters mean. It's historical. So you just call them the S, P, D, or F subshell. The superscript that comes after the subshell letter represents the number of electrons that are in that subshell. Okay, so for the first 20 elements, this pattern is pretty straightforward. For hydrogen, it has 1 electron. So 1s1. Helium has 2 electrons. It has 2 protons. It's neutral, so it has 2 electrons. And order of doing this stuff is to always, always, always fill the 1s level first. So 1s2, this subshell is now full. This orbital is full, and helium behaves like the other noble gases. It's happy and content. It doesn't want to lose electrons. It doesn't want to gain electrons. Starting the second row, the second period, the second energy level. Lithium has 3 electrons. We always fill the 1s orbital before we do anything else, which is basically helium, right? 1s2 is basically helium. So that's kind of a shorthand way that you'll see on occasion, like on your TI graphing calculator app. It'll list the noble gas that's immediately above the current element. So for lithium, it might say helium, and then after that, 2s1. Beryllium has 4 electrons. Always fill the 1s orbital first, so 1s2, 2s2. The next element is boron. Boron has 5 protons. Neutral boron has 5 electrons. Always fill the 1s orbital first, 1s2. Next, the 2s orbital gets filled, 2s2. I still need to put 1 electron in a bed. I begin filling the 2p subshell. So 2p1. Carbon with 6 electrons would be 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. Neon, 1s2, 2s2, 2p6. Notice this level is now full. Every subshell is full. Every orbital is full. Neon is happy. It is a noble gas. It doesn't want to lose any electrons, and it doesn't want to gain any electrons. It is very non-reactive. In terms of this analogy with the house, the question you might ask is, what happened to the 3D subshell? Right? We just did neon, 1s2, 2s2, 2p6. That means we just filled the first two floors of this house. 1s2 on the bottom, 2s2 on the left of the second floor, 2p6 on the right on the second floor. When we go the next floor up, we skip the 3D subshell until after we fill in the 4s subshell. And that's not the only change. Yikes. So instead of appearing in the nth energy level, it's appearing in the n minus 1th energy level. Craziness, craziness. Here's a slide attempting to just remind you the periodic table has all this information on it. Not too useful for us. Sadly, this is the last slide on this PowerPoint, and by itself, it's not giving you very good examples of the electron configuration. I want to point out to you that if you happen to have a TI 84 plus or better graphing calculator with the apps installed, you might happen to have an app for the periodic table. If you do, and you fire it up, and you move your cursor to atomic number 26, which is iron, and press info, it'll list iron as atomic number 26, the symbol Fe, the weight 55.845, which matches my printed periodic table for iron. They list neutrons as 30. That would be for the most frequently occurring isotope. Number of protons is 26, of course. And then underneath that, it says in square brackets, argon. After that, it says 3d6 4s2. The argon is a shorthand way of saying do the complete electron orbital configuration of the previous argon noble gas. The electron configuration of the previous noble gas in atomic number. Then, after that, do the rest of the electron configuration. That's where it says 3d6 4s2, which I would express as 4s2 3d6. So be aware you do have that as an app on a TI, some of the more advanced